So you can't study metabolism for more than like 30 seconds before encountering metabolic pathways. And so in this video, we're going to ask ourselves, well, what is a metabolic pathway and how do we even think about them? So there's a million pictures like this. I think I've already shown some of these in videos where you just have this map of all of these cool pathways that cells do, and all these things, these chemical transformations that can happen in form. And in some sense, metabolism, as it's normally taught, is digging into and understanding each of these pathways. And we are going to do that. We're going to go and look at specific pathways like glycolysis and the pentose phosphate pathway. But the goal of today's video is to try to just wrap our heads around what are these things that we're drawing. So as an example, I'm going to use this sort of throughout the rest of this video. This is a pathway that we're going to study in detail later, but this is the pathway of glycolysis. This is actually only part of the pathway, but basically what this involves is you take a molecule with some carbon and a phosphate hanging off of it. You've got some other molecules it interacts with. That does a small chemical transformation, right? If you look carefully at this, what you'll see is we're taking a phosphate from solution and we're sticking it onto the carbon, and we actually did an oxidation reaction here. We oxidized a carbon. We then can take a phosphate off, say, and make an ATP. So we took this phosphate off and we made ourselves an ATP. We can do chemical transformation where we're going to move the phosphate up here to this position. So we did a transformation. We do another sort of rearrangement where basically we're doing what's forming an enol. And then finally, we can take an ATP, an ADP, and take this phosphate off to make ATP, right? So there's this idea of, oh, look, we just did a linear set of steps. We started out here, and then we went from there to there to there to there to there, right? Just boom, boom, boom. And you can imagine this is like this mechanical machine that's proceeding step 1 to step 2 to step 3 to step 4. But when you think about a cell, right, what we should actually think about it, there's other ways you can think about it, right? So this is just a bunch of different molecules that are thrown into a cell, and they're all bouncing around. They're all totally randomly scattered everywhere. And if we imagine doing a simulation where we describe each of these as a circle and just watch them bounce around, what you see is this random diffusive process, right? There's no brain that's saying, oh, A needs to become B, needs to become C. Instead, it's just all bouncing around randomly. And how in the world can we go from these two pictures of molecules everywhere to molecules bouncing around into the idea of a metabolic pathway? And so, yeah, what are these things? And what I'm going to point out in this, I'm going to give you 4 different things that together define a metabolic pathway. A metabolic pathway is a linked set of reactions. A metabolic pathway is thermodynamically favorable. A metabolic pathway connects a source to a sink. And a metabolic pathway is fast enough to matter. So let's go into each of these in turn. So first, a metabolic pathway is a linked set of reactions. So this is a good point to pause, actually, if you want to think about it instead of just having me talk at you. I've got a set of reactions here, 3 different reactions. And what I'd like to do is write out a single reaction that describes how do I get to H if I start from A. So I'm going to start with A, and then I'm going to turn that molecule, and I'm going to generate a molecule of H. So good chance to pause and actually try to do this yourself. So if you have a chance, hit your pause button. Great, you paused. We're coming back. Let's talk about what I would do for this. So I'm going to do this on the next slide. I've got this top reaction, A plus B goes to C and D. I can then take the next reaction, a C plus E going to F. What I'm going to do is I'm actually just going to put this and this on the products and reactants side of the reaction. What that lets me write out is something like this, where now I've got A, B, C, E going to C, D, F. But then I can recognize C is on both sides and I can cancel that. And basically what I've done there is I've said I'm going to take the molecule of C, I'm going to take the molecule of C that's generated here. I'm going to combine it with a molecule of E to generate a molecule of F. So I basically took this thing and jammed it in for that C. Okay? That gives me this net reaction. A plus B goes to E, goes to D and F. I lost the C because the C is the product of A plus B, and it's the reactant of C plus E. This is a linked reaction, right? We've linked using C these 2 reactions to each other. Now let's think about G plus H goes to F. Remember, I'm trying to get to H. That was the prompt, so we want to start with A and get to H. This is now on the product side, so we can just flip that over, right? We can define in a reaction whichever way we want. So now I'm just saying I'm going to think about this as F going to G and H. If we do that, then we do exactly the same move as before. I'm going to stick F on this side, and I'm going to stick G and H on this side. And what you'll notice if you do that is F cancels. F is the product and reactant. So we're consuming a molecule of F up here to make a molecule of H. And that yields us a total reaction of A plus B plus E goes to D plus G plus H, right? So this is a one large reaction that's built out of linking three smaller reactions. And we can write this in a couple of ways. So this is the net reaction, we could say, just as I've shown it. So we've got these three reactions at the top. You link them together and you can generate this here. The other way we will often draw this in biochemistry is something like this, as a pathway. And so I'm going to make myself go away, which is this button. There we go. That A plus B kicks off a molecule of D and makes a molecule of C. So that's right here. C then comes in with a molecule of E to become F, and then F can become G and H, right? So this is an entire pathway that we've written out. And notice what you'll see on this is A, B, and E, they're all on the net side here, right? They're all consumed by this reaction. Whereas D, G, and H are the outputs on this side of the reaction. So actually, this is generally how you'll see things written in biochemistry, but ultimately you can think about this as, no, we're linking a set of individual reactions, and you can think about it as just one giant reaction where the products and reactants that are consumed, in this case the C and the F, just completely disappear, right? They're not relevant to understanding the overall, say, directionality of this reaction. Okay, so when we say that metabolism is a linked set of reactions, that is what we mean. We've linked a bunch of different reactions together, taking the products of one reaction, making them the reactants of another. Next thing about reactions, what is it? Well, there's something that's thermodynamically favorable. And here, we're getting into things like free energies and delta G's, everybody's favorite. So let's do an exercise with this, and then we're going to think about it in the way I like thinking about free energies, which is probabilities. So here now I've added some information. I've said that under the conditions that we observe in a cell, we can calculate or we know the free energies of the free energies of these reactions. And what we say is, the free energy of this reaction is minus 10 kilojoules per mole. This one's minus 15 kilojoules per mole, and this one's minus 5 kilojoules per mole. So what is the overall delta G for this reaction? So again, this is a good point to pause and think about it for a second. So pause. Unpause. So what is the overall delta G going to be? Well, I have this reaction, A plus B, going to C plus D. That is preserved, right? So my overall delta G equals minus 10 at that reaction. And then free energies are what's known as a state function, but basically means you can just add them up in this case. So we can say, all right, well, what's our next reaction? Our next reaction is C plus E goes to F. We don't flip that over or anything, so we just say, all right, our delta G is plus minus 15, right? So we're adding those two delta G's. And then over here, remember we had to flip this reaction over. We had to go from G plus H goes to F. Remember we flipped it over to make this reaction balance. So F was now our reactant and these were our products. To do that, we just have to flip our delta G. So we're going to subtract minus 5 because we had to flip that reaction over. If it's minus 5 kilojoules per mole to go this way, it's plus 5 kilojoules per mole to go this way, right? This is the symmetrical idea of free energies that they're if we think about it as a bet, there's some probability of going forward. That's the opposite of the probability of going backwards. Okay, so you add those numbers up. That gives us a delta G of 20 kilojoules per mole minus. So it's minus 20 kilojoules per mole to go from here to here. Cool. What in the world does that mean? I like thinking about these in terms of a bet. And under these conditions, it is more probable that a molecule goes from A to H rather than from H to A. So if we just looking at a molecule in the system, we would expect to see A going to H more often than G going to H. And we can actually calculate that using this expression I've actually shown a couple of times, make myself go away again, where basically we can say what's the probability of forward over the probability of reverse. It's given by this thing. You plug in the numbers here and you get this number. It's 3,000 to 1 favoring going from A to H rather than from H to A. Or another way to put it is for every molecule of A that goes, every molecule of H that goes to A, that goes backwards, we're going to see 3,000 molecules go forward. So when we say a reaction is thermodynamically favorable, what we're saying is the net flow is going to be A to H rather than H to A. And we can think about this actually, going to go away again. We're going to think about this actually as the product of a set of bets, right? That was for the entire reaction, but we can think about this as each bet by itself. So here's the bet that you go from A plus B goes to C plus D. Here's the bet going from C plus E goes to F. Here's the bet from going to F to H, right? If you plug in those delta G's, which remember were minus 10, minus 15, and this is plus 5, right, to run backwards. You can plug those in and calculate their individual probabilities. Those probabilities end up being 56 to 1 forward for the first reaction, 424 to 1 for the second reaction, and actually 1 to 75 opposing going backwards for the third reaction. But if you multiply all these together, you get, no, it's 3,000 to 1 favoring going forward over reverse. So when we see, say a reaction is thermodynamically favorable, what we're saying is that the probability of going this direction is higher than the probability of going this direction. Here's the example that I showed before for glycolysis. Let's take away some of the reactants so that our brains don't explode. If you look under a particular set of cellular conditions that's plausible, what you can actually get is the set of probabilities of going forward and backwards. So for example, this reaction is actually slightly unfavorable. It's 1 to 11 going that way. It's 1 to 5, so it's slightly unfavorable to go this way. But then this particular reaction under these conditions is 1,000 to 1 favorable, slightly unfavorable, about 195,000 to 1 favorable going that way, which if you multiply these steps together, step 1, step 2, step 3, step 4, step 5, you get overall, it's a 200,000-fold preference for going forward versus backwards. This is a thermodynamically favorable pathway because the total product of the probabilities of all of the reaction ends up saying, no, our molecule, if we just watch long enough, we're going to see more things going this direction than that direction. Okay, so a metabolic pathway is a set of linked reactions. The reactants from one, or so products of one reaction become the reactants in another. And it's thermodynamically favorable. If we had to bet that which direction it's going, we're going to see net formation of products rather than the other direction. Another feature of metabolic pathways is they always connect a source to a sink. And we saw this when we were talking about the definition of metabolism and things like steady state. So if we think about water that's flowing down a river and filling up a dam in the middle, this right here might be a step in our metabolic pathway. This is Dexter Reservoir, right? So it's full of water at a particular, filled to a particular depth. But it's connecting a source up here of water, source, there's a C, to a sink, right? There's water continuously coming in from the source. These are, the mountains in this case of this river. And the sink is the Pacific Ocean. And so there's a source of material and a sink, and then whatever's happening in the middle is a steady state that is in the middle of this relaxation or this flow or this equilibration for going from source into sink. And we saw this when I showed this example of sort of tanks and pipes. So this up here would be our source. It's a reservoir, say, full of water. And then this would be our sink. This is where the water is flowing to. And in metabolism, what we see is basically this process of material always continuously flowing source to sink, whatever weird stuff is happening in the middle. And the reason that that's important is because of the source and sinks, reactions are always equilibrating, but are never at equilibrium. This is another way of saying that the delta G for the reaction is less than 0, right? It's favorable going forward. Well, the only way that can be met over time is if you continually are making the reactions go out of equilibrium. You're continually dumping in fuel. It's keeping the reactions so that it's favorable to go forward. If you didn't have this continual input, the system would equilibrate and your delta G would go to zero, and then you would be dead, right? So metabolism is always, as a whole, a metabolic flow of energy and material through cells, and the same exact thing holds for pathways. They always have to have stuff coming in at the top of the pathway and stuff coming out the bottom. They have to have, in the example we've shown with glycolysis, they've got these carbon molecules coming in the end and carbon molecules going out the back. Okay, last one, we're actually almost done, is that metabolic pathways have to be fast enough to matter. And what do I mean by that? Well, you think about it, metabolism is a competing set of reactions. So I did this as A plus B going to blah, blah. This is the reaction that we showed before. I didn't put on there, well, maybe A actually can also become Z, F can become Q, and G can become, I don't know, Y, right? Every one of these molecules is going to have some other metabolic pathway that it can become, some other metabolite, some other place it can flow. And what that means is, as a whole, when we're thinking about the reaction, if this reaction is going to happen, it has to be fast enough to compete with all of these side reactions. Let's look at this. Another way you can say this is a metabolite in a cell, because this is out of equilibrium, is always equilibrating, it is always going to become something else. The question is, what will that metabolite become? And a particular pathway of a place that this metabolite can go or something can become is only relevant if the reactions it does are fast enough to compete with other reactions. So a good example of this is actually something we've briefly mentioned in previous videos, but this is a molecule of glucose 6-phosphate. This is a key metabolite that is in our cells. It has multiple places it can go, right? So it can undergo this isomerization reaction, and this is going down the pathway of glycolysis. It can lose a phosphate, so there can be hydrolysis of this phosphate off. This is going to actually gluconeogenesis, right? So it can lose that phosphate. It can be converted into glucose 1-phosphate, and this is on the way to glycogenesis. Or it can be oxidized by glucose 6-phosphate dehydrogenase, and this is on pathway towards the oxidative pentose phosphate pathway. Right? These are 4 metabolic outcomes from this single glucose molecule. And where that glucose molecule goes depends on which pathways are fast enough. And which pathways are fast enough actually turns out to usually determined by whether the enzymes are around. So, for example, liver cells love doing this reaction. This is one that they do all the time, gluconeogenesis. But most cells don't actually make this. And so this entire pathway is not possible in, say, a muscle cell, because muscle cells don't have this enzyme. They're not making this enzyme, so they can't do gluconeogenesis. This pathway is thermodynamically favorable, right? It's a possible outcome. Chopping off that phosphate is a favorable thing to do, but it's too slow. So it just doesn't happen. So inside of anything but a liver cell, you're going to see all this other cool stuff happening, but you will never see this because it is too slow without the enzymes that are present. Okay, so what have we said? We've said that metabolic pathways are these linked set of reactions where the products of one reaction are the reactants of another. It's a thermodynamically favorable reaction where we can actually know that going from the product side to the reactant side is favorable across multiple steps. It's going to connect a source to a sink, so there's always going to have to be stuff that can come into the pathway and stuff that can come out. That maintains the system out of equilibrium, which actually makes it so it can be thermodynamically favorable. And finally, these pathways have to be fast enough to matter because there's a bunch of other possible places that those molecules can go, a bunch of other metabolic changes that can happen. So a pathway, if it's going to exist, has to be fast enough to compete. Okay, so that's what I have on metabolic pathways. As we go forward here, we're going to launch into a variety of other things we're going to think about before getting to metabolism. But looking forward just ahead, in a few videos in the future, we're actually going to start looking at individual pathways, like the ones that I hinted at there, glycolysis and gluconeogenesis. What are those pathways? How do they work? But hopefully now you have a lens when we're looking at that. When we're saying glycolysis exists, what we're actually saying is there is a thermodynamically favorable pathway through these metabolites that's fast enough to matter. And then hopefully that'll give you some understanding rather than just having it be a bunch of facts about glycolysis that we have to remember. So look forward to doing that with you. Until then, have a nice time sitting at your desk watching videos about biochemistry.